Okay. Previously, you have seen in LMS algorithm, convergence in mean requires mu to be less than 2 by trace R, where R is the input autocorrelation matrix. Now, suppose input statistics changes from time to time. So, autocorrelation matrix also changes, trace R also changes. So, it will be very difficult to set an upper limit of mu, okay, because upper limit is varying. There the upper limit is independent of things like trace R, which depends on the input statistics. And it is more often we find NLMS used in practice rather than LMS. Now, there are various ways of introducing NLMS algorithms. We will show it from a system identification point of view. Suppose we have an unknown system with two coefficients, just impulse response having two coefficients, say FIR filter, maybe W0 cap, W1 cap, all right. And also we consider no observation noise. So, this basically there is an unknown system xn comes, okay, output itself is dn. Okay. Now, to find out, so there is an adaptation, there is no noise here. So, some adaptive filter which will be basically, these are original coefficients, but when it is adaptive it will use this error, sorry, not this, so this is your dn, so this error and this input, okay. So this is the adaptive filter. We all know this, we have studied this, this is adaptive filter, sorry. Okay, and by this we adapt them. Now, suppose at nth time index we have Wn, that is W0n, W1n. So, we are adapting, so they are not equal to W0 cap and W1 cap, so there is a difference, all right. Now, you see, I do not know the coefficients, but I know there are two coefficients. So, I know in general system output dn will be some general W0 xn and W1 xn minus 1, where W0 and W1 could be W0 cap but W1 cap also, but this is an equation with two unknowns W0 and W cap. Okay, therefore, there are infinite solutions of which one could be this, but I do not know these optimal ones. I know input and output can be modeled like this, because it is a two coefficient FIR filter system. So, output will be in terms of input given by this, where W0 and W1 are the general filter coefficients. So, this is a straight line, right, this is a straight line, and suppose I draw like this is the straight line at nth clock, that is dn is equal to so this straight line contains all the points W0, W1 which satisfy this, and therefore contains this also, because these are true coefficients, they obviously satisfy these equations. So, maybe this is that point. So, this is your W0 cap, W1 cap, this point, this is optimal point. And suppose currently I have Wn, so this much is Wn. well, this is becoming parallel. So, this is Wn. Let me erase this because by mistake I made it parallel. So, why should it be parallel? The original one. True value. Okay. And now, suppose this is your Wn. Wn is the adaptive filter coefficient vector at nth clock, and Wn is, we want Wn to converge to this point as n goes to infinity. So, if what we do in this algorithm, we take a perpendicular, we draw a perpendicular on this point. So, whatever we get, this we take to be the adaptive filter weight for the next clock. Okay, next clock. See, this is now on this line, this is satisfying this. Okay, but in the next clock, the very next clock, I have n plus 1th clock. So, n plus 1th clock will have another equation, d n plus 1 is equal to W0 so you see x data, and here x n plus 1, here it was x n, here it was x n minus 1, here it is x n. So, it is different straight line, the straight line has changed. Okay. So, now this is the model. Okay. At n plus 1th clock, this is the equation. Okay. So, this equation will again be a straight line. Okay. But whether it is nth clock or n plus 1th clock, these equations must be satisfied by the true parameters, because they are true parameters. So, whether I am nth clock, if I am nth clock, W0 true value should be W0 cap, and this is W1 cap, this is satisfied. When I move to next clock, n plus 1th clock, again W0 should be W0 cap, W1 cap, and with that data, I should get dn plus 1. Okay. This is how it is. That means, this may be a new straight line, but this will again have this point, this optimal point common, that is, it will intersect this line at this point. All right. So, that means, this is another line, this is the new one, dn plus 1 is all right. This was not perfectly perpendicular. So, yeah, they are perpendicular. Looks 90 degree here. So, then at the n plus 1th clock, I have this new straight line which contains this optimal point, but I got Wn plus 1 as the updated weight vector from the previous clock. From Wn I generated Wn plus 1, but again Wn plus 1 is not staying here, not a point on this line. So, I again take a perpendicular. I again take a perpendicular, and this will become my, this point will become Wn plus 2 to be used in the next cycle. Now, see one thing, consider this triangle, this is 90 degree, right. As a result, this side, which is a hypotenuse, is longer than this, but what is this? This is the difference between Wn and the optimal vector, Wn and optimal vector, this was the difference. And what is this? This is again the difference between Wn plus 1 and optimal vector. That means this is filter weight vector at length n at time n, and this is filter weight this is filter weight error vector, because W n minus the W opt. So, this is a filter weight error vector at nth clock. And again, what is this? This is a filter weight error vector, that is W n plus 1 minus W opt at n plus 1th clock. And now see, by this process the length, okay, has gone down. That means this point has come closer to this optimal one than the earlier, because as I told you, this is a right angle triangle, this side is hypotenuse, its length is longer than this length, and I go on doing it. So, eventually this length, error vector length, will shrink and shrink and shrink, and finally it will converge on this. This is the philosophy of normalized NLMS algorithm. All right. That means what we are doing is this: we are trying to find out, and one more thing, what is a perpendicular? Because if I could have taken a point here, I could have taken a point here, I could have taken a point here, but this point is where, if I draw a perpendicular on this line, then this is that point. What is that point? The distance between this point and this point, that is minimum, then only this is perpendicular. You take any other point, form a triangle, this again apply Pythagoras, okay, hypotenuse will be longer than this if it is 90 degrees, right. Okay, this is from plane geometry, only when the length is minimum, then this is a perpendicular. Any other point, if I join with this point, okay, that will have longer length than this. Therefore, to identify this particular point, which will be W n plus 1 vector, I should look for a point on this straight line from which the distance between W n, from which the distance with W n, that is this distance, has minimum length. Length means norm square in a general sense, okay, in an n-dimensional sense, norm square. That means I should try to find out, that is find out W n plus 1, so that this norm square is minimum, but W n plus 1 must be lying on that line under the condition is W n plus 1 transpose x n plus 1. Okay, that is an equation actually. If you write, I can write this also as W transpose x n. All right. So, now I have, instead of W, I have brought in n, because I am moving from index to index adapting. So, okay, and this is again W transpose x n plus 1. All right, this is the thing. So, it is not just minimization. If I just have this much, obviously answer is W n plus 1 should be equal to W n, so this is 0. But that is not the thing. I must have W n plus 1 on this straight line. Then which point is closest to W n, so that the distance, that is the norm square, is minimum. That will give me that W n plus 1, right. So, this is called constraint minimization. So, I am not sure how many of you have studied Lagrange multipliers. Suppose given f of x, okay, is a function like this. This is a minima. You want to minimize it, find the minima somewhere or other. This is a minima. All right. This is a global minima, fine, unconstrained minimization. But you are given that minima is f of x subject to the constraint some other function g x equal to say k. So, only when g x equal to k satisfied, this is the x axis, this is f x. Only wherever this is satisfied, you have to restrict yourself to that. So, only that part of this function will be considered, and there you have to find out minima. That means it could be one patch, it could be here, it could be one point, it could be here, like that. If these are the places where your this is satisfied, g x equal to k is satisfied, suppose these are the places. Okay. So, you take the curve only this much, only this much, and only this much, and then find out what is the minima, and this minima is this point, we can see this point. Okay. These are constraint minima, right. So, to do this, to obtain this, what we do? We construct a more general function. Or Lx, which is f x, plus there is a parameter lambda I bring in, which is called Lagrange multiplier. It is a real constant times g x minus k. So, now it is a if x is a scalar, now this is a two-dimensional function. You will have one axis x, another axis lambda, and in that x lambda plane you can plot this. In that plot will become equal to this curve if lambda equal to 0. Okay. So, that means one segment of the plot is given f x, but this is a more general function. Then you try to minimize this. Okay. That means one will be del L del x equal to 0. So, that should be f prime x plus lambda g prime x, k is constant, this is equal to 0. So, you get one equation from here, you can find out lambda from here, okay, one equation. Another is del L del lambda equal to 0. So, del lambda equal to 0 means g x minus k equal to 0, which is my constraint g x equal to k. So, this will be satisfied. Therefore, if I minimize it, that minima point will satisfy g x equal to k. Okay. And then g x equal to k subject to that, I am minimizing, that is g x equal to k is maintained, and then I am minimizing L x. So, I will be basically minimizing f x subject to g x equal to k. All right. Because both have to be satisfied simultaneously, then only L x is minimizing. But if L x is minimized, this point should be satisfied, and under this L x minimized means f x also minimized, because then g x equal to k means this is 0. So, now this is unconstrained, just simply minimize, but then I have got two parameters now. So, here I took x to be scalar, but if it could be vector of many x 1, x 2, x 3 suppose. So, I should have del x 1 equal to 0, del x 2 equal to 0, del x 3 equal to 0, and of course, this. All right. So, this is what I will do here. I will try to find out this guy, I can call it w, is a variable w, I have to find out this, w minus this norm squared, so that the w transpose x n plus 1 is d n plus 1. Okay, this is just for notational simplicity. That means, I will construct a more generalized function L w here. W's are the unknown. Here it was x single parameter, L x. You have got now w as a vector of so many coefficients, in general, say capital N coefficients. So, L will be a function of w, and well, I should also generalize means, I should write it more correctly. I should call it the function of 2, right. So, I will have a more generalized function L which will have W comma lambda. This is a constraint. All right. So, therefore, I take this L W is just standing for W n plus 1. For notational simplicity, I am just making it W, comma lambda. So, this will have the original function first, which is to be minimized, that was W minus W n norm square. Then lambda times that constraint. Constraint is d n minus, okay, because if it is 0, it will be d n equal to W transpose x n. So, that W will be lying on that line and it will be minimized. Subject to that, it will be minimizing this, then only overall is minimized. Okay. Therefore, first is of course del L del lambda, which is this equation. Equal to 0. That is my constraint. Next comes del L del W. Now, we have done this kind of thing, that is actually this is equal to del W L. You remember this notation we used in the context of derivation of optimal filter and NLMS algorithm and all that. It is just nothing but partial derivatives stacked. Okay. So, that will be, that is for that I have to derive it. Now, first consider this term W minus, this is W minus W n transpose. Now, you write in an expanded form W transpose W, which is this W transpose W minus W n transpose W, and of course, we are taking all real, I forgot to mention. Okay. So, W n transpose W and W transpose W n both are same, and W n transpose W n, so norm square. So, if I have to derive it with respect to W, what will I get? This one, what does it give? It is like, if W is W0, W1, dot 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 dot, Wn minus 1, norm square of W is W transpose W, which will be W0 square, W1 square, dot 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 square. So, if I take it partial derivative of this with respect to any W, say W k square, so only this term will come under operation, differentiation operation, and it will be twice W k. So, now we stack all the derivatives, twice W0, twice W1, twice like that. So, it will be 2W. So, this will give rise to 2W, all right, minus 2W transpose Wn. That is obvious, W0 times W0n plus W1 times, okay, that is Wn I am sorry, I should have written it not this way. So, W transpose W n, you can easily see W0 W0 n, W1 W1 n, dot dot dot, and then addition. So, if I differentiate, it will basically kth term will be giving me W k n. So, if I stack them W0 n, W1 n, so basically you get W n. So, from here you get W n, all right, and this is of course independent of W. So, that goes, and this you have to equate to 0. That is, if I apply del W only on this much, okay, this part, but this is, I have got one more term. This is except for, I mean, in relation to W minus W n norm square here, you see there is another term. So, this I will not be, this is just to show that if I was doing unconstrained optimization, I would have got this and W would have been W n, which is what I had told earlier. That is, if there is no constraint, your solution is obviously W equal to W n, because then the error W minus W n is 0. But that we are not doing, right. So, this we are not doing, we are minimizing this whole thing. So, first term when derived will give rise to this, that is now del W L will be twice W minus twice W n, and then I have got another term minus lambda W transpose x n. So, W transpose x n again derived, when derived by the same way, the same logic, it will be giving rise to x n. So, minus lambda x n, and that is equal to 0. So, I take lambda x n on one side, and this W minus W n is lambda by 2 x n. Now, this is a vector equation, W is a vector, W n is a vector, x n is a vector, but from this I have to find out lambda. So, what I do, I take transpose of this transpose. So, this also to be transposed times x n, here I will say lambda by 2, this is to be transposed x n, which is lambda by 2 norm x n square. So, I get lambda from here, okay, I get lambda from here. Lambda is one minute. Lambda is 2 into 2 into W minus W n transpose x n by norm x n square. Now, one thing you see, from this constraint, when you derive with respect to lambda, the same thing, you get d n equal to W transpose x n. That means, W transpose x n equal to d n, that constraint. That means, W transpose x n is d n, right. That means, this is equal to twice d n minus W transpose n x n by norm x n square. Now, what is happening in the filter x n, and I have got this W n. So, output is right. This we know, W transpose n times input vector. So, this thing, if I subtract as I am doing here, d n minus this filter output, this is my good old filter output error, which is used for adaptation. I am calling it E n. So, it is twice E n by norm x n square. This is lambda. Therefore, if I bring it back here, use that lambda here, then what I get? Okay. W I keep on the one side, Okay, so W and Wn and this term on the other side. So W will be Wn plus lambda by 2 xn, right? So W, which is equal to actually Wn plus 1, I just use the notation W here. It will be Wn, okay, this is equal to 0. So Wn plus lambda by 2 xn. And now lambda, if you substitute here, this 2 and 2 cancels, En by this, En is a scalar, so xn, okay, lambda I am replacing, so 2 and 2 cancels, En xn, En is a scalar, so En I am writing later, does not matter whether I write, by norm xn square. This is the basic NLMS algorithm. Then we will work further on it and modify and interpret. That is the next class. Thank you very much.